Quality Control and Improvement, Module 6, Lecture 1, Control Charts for Attributes. Language objectives for Lecture 1 are to design attribute control charts to analyze a business or manufacturing product, analyze an attribute chart to detect when the process is in control. Reading assignment is Chapter 7, pages 265 to 311. To understand how to plot the control charts for attributes, it's important to understand exactly what an attribute is. Attributes are discrete in nature, which means that they don't have decimal points. They're simply a number, or they're a binary decision, a yes or no. For example, if you have a carton of light bulbs and you count the number of light bulbs that are non-functioning, so maybe you have an assembly line, you're producing cartons of light bulbs, thousands of cartons a day of light bulbs. You go out on your assembly line and you sample a discrete number, maybe 5 an hour, off the assembly line. You open the cartons and you test the light bulbs, and you count specifically how many light bulbs don't work in that particular pack. Or you can have something like, the proportion of broken eggs in a carton. So for example, again, if you have an egg assembly line, you're producing cartons of eggs. You go out and you pull a certain number off the assembly line. But in this case, instead of just counting how many eggs are broken, you maybe could do a fraction. You could say, okay, 2 eggs out of 12, and so that'd be 2/12. 1/6 of that carton is broken. So you have 2 ways to do it. You could either count the number that are defective, or you do a proportion and use that as your number. And we'll talk about the different types of attribute charts. Some of that comes into play when we try to decide if we want to do a count or we just want to do a fraction. So when are attributes used? Well, attributes are used typically where measurements are not possible, or where measurements can be made but are not because of time, cost, or need. There are 4 types of attribute charts: the P chart, the NP chart, the U chart, and the C chart. In this lecture, we'll talk about the P chart and NP chart, and in the next lecture, we'll talk about the U chart and the C chart. The choice really depends on whether you have a problem with defects or whether you have a fixed or varying sample size. So first, let's talk about the P chart. This is probably the most widely used chart for attributes. It's used to measure the proportion of items in a sample that are defective. Examples are the proportion of broken cookies in a batch, or the proportion of cars produced with a misaligned fender. In order to use the P chart, we have to calculate what's known as the fraction nonconforming, given by the symbol P. This is calculated using N, the number of inspected items, and NP, the number of nonconforming items found. So again, going back to our egg carton, if we open up our egg cartons and we find 2 of them that are broken, well, NP here is 2, and then in our sample is going to be 12. That's the number of items we actually inspected. NP is the number we found broken. So P is going to be a fraction. Maybe 1/6 in the case of the carton of eggs. The P chart control limits are calculated. Once we calculate what P is, we can simply calculate the upper control limit and the lower control limit using the following formulas. So let's take a look at an example of P chart. This is the best way to learn how to use the charts, is to actually look at examples. So we're going to look at example. We're going to calculate the control limits from the center line by hand, and then we're going to use Minitab to actually do the work for us and actually plot the results. But it's really important to understand how to calculate the center line and the limits by hand to understand what Minitab is doing. That kind of gives you a check on you can kind of make sure that you're actually entering in Minitab correctly if you actually are able to kind of pre-calculate and check the control limits are actually what you wanted. So in this case, a production manager at a tire manufacturing plant has inspected the number of defective tires in 20 random samples with 20 observation each. Construct a 3 sigma control chart from the data. So here we have the sample number. We took 20 samples. In each sample, we selected 20 tires. And so again, this is a tire manufacturing facility, and it's manufacturing hundreds and hundreds of tires an hour. So every hour, maybe we go out and we select 20 tires off the rack. So you have to sort of kind of in this kind of case that we took 20 samples maybe once every hour. And each sample we selected 20 tires. Now this doesn't necessarily have to be the same. I mean, you can have we could have done 24 samples on like 20 on a 24-hour period every hour and pulled off 10 tires. So don't think that the sample number and the number of observations sample have to be the same because they don't. But let's say, for example, on the first hour we pulled off 20 tires and we had 3 defective. So the fraction defective in this particular sample batch would be 3 divided by 20 is 0.15. Next hour we pull off 20 tires. We have 2 that are defective. 2 divided by 20 is 0.1, and et cetera. So we just continue this for the entire 20 samples that we take. So the number of defective tires, we can simply add up this column. We get 40. Number of observation sample, well, we did it, in this case, 20 hours times 20, 400. Then once we have those computed, we can calculate P bar, which is the percentage. So the total number of defective tires was 40. Total number of observations is 400. So we divide these, we get 0.1. And from there we can calculate our control limits. Sigma P here is P bar times 1 minus P bar. P bar is 0.1. And 1 minus P bar is 1 minus 0.1 or 0.9 divided by the square root of n, which is 20, which is 0.067. So our upper control limit is P bar plus 3 times sigma P, 0.301. Our lower control limit is P bar minus 3 times sigma P, which we actually get a negative number, and we set that to 0. So once we have entered the data into Minitab, and what I did is I entered a single column with the number of defects. You go to Stat, Control Charts, Attributes Charts, P, and then enter your data into to Minitab. For example, I have my column selected, so I just selected the first column. I labeled it defects, is what I labeled it. The subgroup sizes, I entered 20. Hit OK. And Minitab will automatically calculate the fraction and control limits for you. And here you can see that Minitab gets 0.3012, and which is what we had. We didn't have that. We didn't carry the extra decimal, but the extra digit here. And it gets 0 here, and it plots a P bar. And you can see it plots the proportion versus the samples we've drawn. We drew 20 samples. And you can see the chart kind of falls along. There's really nothing that's out of control here. It's bouncing around. There's no, nothing exceeds the upper control limit or lower control limit. And I don't see any obvious patterns here. Looks like everything's in control in this particular example. Okay, so let's look at the NP chart. The NP chart is similar to the P chart, but it's an adaptation of the P chart that tracks just the number of non-conforming products. It eliminates the calculation of P, the fraction non-conforming. The NP control chart limits are given by the following formulas. First, we calculate the center line, then we calculate the upper control limit and lower control limit. And instead of explaining these mathematically, I think I'm going to show you how they work in a formula. It's or in a particular example. I think it's you'll understand a lot clearer how to apply these. So let's take a look at our example. A company receives shipments of circuit boards from its suppliers. They keep track of the number of damaged, incomplete, or inoperative circuit boards. These circuit boards are randomly selected from each truckload with a sample size of n equals 50. Plot the number of non-conforming units on the control chart. So here we have, it's the subgroup number maybe we did these once an hour all the way up to 20 hours. In here's 50. We randomly selected that we had sample size of 50. And then we count the number of non-conforming units. So in the first subgroup, we had 4. The second subgroup, we had 6, etc. So let's say we calculate the center line and control limits by hand. Again, Minitab will do this for us, but it's always good to check this. And it's good to know how it does this, so that you know that Minitab's not performing some kind of magic. It's just doing the math grunt work for us. So NP bar, this is calculated as the sum of I equals 1 to n of the number NP divided by m. So in this case, m here is 20. This is the subgroup number, is the number of subgroups we have, which is 20. Sum of I equals 1 to n of NP, that's simply adding up this column of the number of defectives. So 4 plus 6 plus 5 plus 2 all the way down. That's going to be 73. So you write these, you get 3.65. That's NP bar. P bar is simply the probability of one of those being bad. So it's the sum from I equals 1 to n of NP. So what are we doing here? Well, we're simply adding up all of these NP values. So in this case, it would be I equals 1 to 20, summing all these up. So it would be 4 plus 6 plus 5 plus 2 all the way down to 2. So if you add all those up again, you get 73. Sum from I equals 1 to n of n, that's just counting up this column here, the second column, 50 plus 50 plus 50, so all the way down. So it's 50 times 20, because we had 20 subgroups, so that'd be 1,000. So the probability of one of those being bad is 0.073. Then to find the upper control limit and lower control limit, we're going to use the following formulas. So NP we calculated, that's 3.65, plus 3 times the square root of NP times 1 minus P bar. So you calculate these, you get 9.17. That's the upper control limit. The lower control limit is calculated similarly. The only difference, you have a minus sign here. So when you calculate this, you get minus 1.87. And so since this is less than 0, we just set it equal to 0. So in Minitab, once you have the data entered into a single column, you simply go to Stat, Control Charts, Attributes Charts, NP, and then Minitab will calculate the control charts for us here. You can check the upper control limit. It's what we calculated, 9.17, NP bar 3.65, and the lower control limit is 0. So again, looking at this chart, it looks like the chart's under control. The points flow smoothly back and forth across the center line. The number of points on each side of the center line are balanced, with the majority of points actually being near the center line. There's no trends, runs, cycles, or sudden shifts in the apparent level. And all the data points fall within the upper and lower control limits. So we would say this process is in control.